I have no idea what he just said, but I hope it's good. So I'm from America, and I want to be honest with you this morning. In applying for the visa to get here today, there were a few hiccups along the way. In fact, at some point, several points, I was like, maybe this might not actually happen. In the end, it took more than a full day of my work, as well as someone in America, someone in Israel, and several people in Russia to make this happen. And looking at the crowd here today and seeing the lineup of talks, and also the hospitality shown to me by Roman. Where's Roman? Hey, last night, yes, I would do it all again in a second. Thank you for the invitation to be here. It is an honor and privilege to speak for the first time to the Russian Scala community. Thank you. So this morning, good morning, I'm going to be talking about upgrading your future. And of course, I mean the future in the Scala standard library, right? But I also mean your future and the future of your company. I'm going to make a case this morning that there are techniques in functional programming that if you pull over and you make accessible, they can solve the problems that you already solve in your day job, but they can solve it in a way that you could never do with other approaches. So today, I'm going to start off my talk by discussing the problem. Why do we have future in the Scala standard library? Why do we have functional alternatives to future, like the library Zeo, which is one of the open source projects I work on? And then I'm going to talk about, I'll dive into a head-to-head comparison between Scala's future and the data type in the Zeo library that I work on to show you, point for point, how these two things stack up to one another. And finally, I'll talk about, if I've interested you enough by the end of the talk, I'm going to discuss how you could experiment with Zeo in your own project and possibly start to upgrade your use of future to something that has benefits that you'll pay for itself many times over in modern application development. So my story today actually begins way back in 2005. That's about when Moore's Law died. So prior to that point in time, every 2 years or so, CPUs would double in speed. That was the good old days when our games got faster and we could afford to write slower and slower code and the CPUs would just catch up for us. But unfortunately, something happened right around 2005. They hit the limitations of physical manufacturing. They couldn't make the CPUs any faster. That didn't stop them from continuing to add transistors, but instead of making CPUs faster, they started adding more cores. And that's why you can buy a desktop machine today that has 32 cores. And you can buy server machines with even more cores than that. As application developers, one of the things that we try to do is minimize application latency and maximize throughput. And that means that if we want to do this in this day and age in which CPUs are not getting any faster, we have got to write parallel code. But it's not enough to just write lots and lots of parallel code, because we can create many, many threads. Operating systems in the JVM, they allow us to create hundreds or thousands, tens of thousands of threads, even if our physical machine only has a few cores. It's not enough to just create a bunch of threads. We need to pay attention to the limitations of the underlying hardware. In this figure here, you can see what happens if we have a 4-core machine and we try to do a bunch of CPU work on it. If we try to create more threads than we have cores, then it doesn't get faster. Not surprisingly, it actually gets slower. And that's because it takes a lot of work for a CPU core to switch between different threads. There's a lot of effort involved in doing that. And so throwing more threads at a problem is not necessarily going to make your problem faster. In fact, in many cases, it'll make it slower. So in the ideal case, you do write parallel code, but you don't write code that's too parallel. You respect the limitations of the underlying hardware. We have a lot of code that looks like this in our Scala code bases and Java code bases. And the reason is actually legacy. Code like this, for example, the first line there sits around blocking the thread that calls the read function for an indefinite amount of time until the information has been read from the input stream. And this code down here, which executes a SQL query against a database, it too blocks. It just sits around waiting. Both of these examples, what they do is they basically put a thread to sleep. And while that thread is sleeping, it's still consuming resources. It's pre-allocated stack size, JVM level resources, operating system level resources. So if we didn't need yet another reason to not use too many threads, it's that a lot of the code that we write for legacy reasons just sits around doing nothing. It consumes the resources of a thread without actually doing any productive work. This is blocking code. And this blocking code has led to a whole style of programming called asynchronous programming. And in asynchronous programming, we don't just block threads sitting around doing nothing. What we do is we hand code a callback, and that code will do its processing or read some information, and then when it's done, it's going to call our callback and allow us to do something with the result. That's async code. And async code is considered to be a best practice, and we've witnessed in the JVM, we've witnessed this huge shift back from the days of blocking libraries to slowly one by one, Netty and Jetty and all the libraries, they started going async because they got tired of sitting around wasting threads. You can get up to about 10,000 threads on modern hardware, and after that, you start to, the overhead of all the threads starts to bog you down so much. So to get beyond the so-called 10K barrier, more and more libraries and applications have switched over entirely to asynchronous programming. So we want to write parallel code. We don't want it to be too parallel because we don't want to just create a bunch of threads that are going to be causing our cores to be doing a lot of context switching. And we don't want to create threads that we're just going to waste, that we're going to park sitting around doing nothing. We want to write async code, basically. And all these three problems are the very same ones that Scala Concurrent Future was invented to solve. And actually, it does a pretty good job solving them. If you want to write parallel code by hand using Java lang thread, you end up with something that looks like that. And this is a very simple example using basically state-of-the-art features from Java util concurrent, like a countdown latch. Back in the good old days of concurrent programming with a JVM, there was none of that stuff. I don't know how many of you are old JVM programmers. You've probably written code like that. That's not very pretty, but if you switch this over to using Future, you can actually do a bunch of things in parallel just by mapping over a list and sending everything in the list to the Future apply constructor where you evaluate it. And that cleans up tremendously on the sort of low-level, just boilerplatey mess that you used to have to do back in the days of Java concurrency. Asynchronous code, it's a similar story. This is what async code looks like natively. So when you're calling these functions and you have to give them callbacks, then what happens is inside your callback, you might have to call yet another asynchronous function. And inside there, you have to give it another callback, and so on and so forth. And you end up building this deeply nested tree-like structure. And this isn't even the worst part. I mean, this is a bit of an eyesore, right? And it's not fun to write code like this. But the worst part about code like this is that if you want to propagate information from somewhere down there to up at the top, oh boy, that is super difficult. To propagate information from an inner level to an outer level. People use all sorts of nasty, unreliable, race condition prone tricks to do that. And Future came along and it let us clean that code up. I mean, for example, you can do the preceding slide in a few lines of a for comprehension, and yeah, for comprehensions aren't very obvious, but you can learn that syntax, you can learn what it means, or you can call flat map a bunch of times yourself, and you end up with something that reflects the linear structure of what's happening. There are no callbacks in this code. We verify the user, we get the roles, we log the access, and then we return the results. This code better reflects our intention and has no low-level mechanics of asynchronicity baked in. So what's the problem with Future then? Well, it's 10 years old. It's been around for a very long time. And it was incorporated into the standard library. I like to say that the standard library is where promising code goes to die. Because once you put something in the standard library, it can't evolve anymore. Because if you change it too much, you'll break all the code out there. And now I'm willing to bet that in this room, probably 80% of you have used Future, and probably 100% of you have Future in your code base, which means they can't just change the API on you. It'll break every single user in the Scala community, and that's not good. We want stability from the things inside our standard library, but stability comes with a cost, and the cost means Future is no longer innovating. And 10 years, it's a long time. We've had a chance to learn. We did something with Future, and now we have a chance to learn from Future and build on it, making sure not to repeat the mistakes of the past, build to a new level of abstraction that solves the problem with Future, the problems with Future, and gives us something that's more suitable for modern application development. And that's where this library called Zeo that I work on is positioned. So in a nutshell, Zeo is a better future. It's more than that, as you're going to see, but it's designed to help you build modern applications, which by their very nature are always going to be asynchronous and concurrent. Due to changes in the way CPUs are now made, we don't have a choice as programmers. If we want to build modern applications, they will be asynchronous and concurrent if we want low latency and scalability and so forth. And if we're going to build them, we need a solution, whether that's Future or something else. Zeo is trying to be the better future, the one that helps you build modern applications with very strong guarantees and learning that comes from having a decade of real-world field experience with Scala concurrent Future. I went back and forth on whether or not I should include this comparison chart between Future and Zeo. It seems harmless enough, but I swear this chart will get me banned from some places. What does the Russian Scala community think? Is it okay for me to have this chart in here? Yeah? All right, good. All right, so let's dive into point-for-point comparison between Zeo and Future. And we're gonna take a look at concerns that matter to you, stuff that you've run into yourself. And we're gonna see how Zeo takes and improves upon what we did with Scala concurrent Future. So Zeo has no implicits. And if you look at Future-based code, it's very common to see this implicit execution context thing threaded through the entire program. And that's best practice, by the way. Importing the global execution context is not considered best practice for very good reasons, because it takes away control from the caller of that code where that Future runs. So ideally, in an ideal world, you thread execution context through your entire program except where you know a Future needs to run in a given execution context. And that is just a lot of pain. I mean, there's nothing wrong with it, right? But it's a lot of pain, it's a lot of typing, it's a lot of boilerplate. Passing around that execution context and making sure it's available implicitly in scope on every single operation that you call on Future, it's a big pain. And with Zeo, there is no execution context. There is no implicit parameter, there is no threading of information through your whole program. You just write ordinary code, no implicits. Another implication of this that is, I think, less appreciated is that because Future's operations always require an execution context, what that means is where your Future runs, which thread pool it runs on, is highly sensitive on lexical scoping. In other words, you can copy-paste code from one code block to another and change where that Future is going to run. Not only that, you can change an import at the top of your file, and suddenly your Future is off running somewhere it shouldn't be. And this bites people in production. They copy paste code, they move stuff around, they do some seemingly benign refactorings, they change an import statement, and suddenly they've got the wrong code running in the wrong location that's leading to exhaustion of some resource or deadlocks or other sorts of very hard to diagnose problems. And there's none of that with Zeo. So what Zeo does is, if you want an effect, a feature, if you will, to run on a specific location, you call an operation called lock. And lock lets you specify this thing should be locked to that specific execution context. And this composes horizontally, which means if you have different parts of your code that need to run in different locations, you can lock all those places, all those pieces of your code where they should run, and then Zeo, as it's executing that, will go ahead and shift the computation to the appropriate thread pool at any point in time. It helps you keep code where it's supposed to be running and makes it stable in the presence of refactoring, so you can move stuff around between different files without changing its meaning. You can change imports at the top of your file without having to worry about breaking your code. Future makes it very easy to write parallel code, almost too easy. And the reason for that is, if you have ever tried to map over a list of stuff and turn it into a future, you've probably encountered an issue in production when that list grew too big. Submitting 100,000 things to a thread pool is never a good idea and can take down almost any production server. Future doesn't give you an easy way to control this parallelism. Everything is implicitly parallel with future, and there's no knobs you have of dialing that back. With Zeo, there's explicit and precise parallelism. If you want to do something in parallel, for example, collect all par is the operation that will do that, and you can call collect all par n to limit the amount of parallelism in that operation. So at every single point, you have explicit control. Do I want parallelism here or not? And if I do want parallelism, do I really want to make it unbounded, or do I want to limit it to, for example, the number of cores in my machine? Future has this primitive called await.result. And I often say that any occurrence of this in your code base is a bug, because it is. Sometimes we have to use await.result. But remember, Future is designed for asynchronous programming, asynchronous and parallel programming. If you're going to block on an async computation, it's as if you weren't doing async to begin with. So basically, this not only undoes the benefit of using asynchronous futures, but also it leads to deadlocks. And more than deadlocks, it leads to a lot of wasted computation. Because what happens when that timeout is reached is the future continues to execute in the background. It doesn't stop. There's no way to stop a future. They just keep on going on and on. And so if you use this code, not only have you opened up possibility to deadlocks and circumvented some of the benefits of async programming, but also you've created background threads that are off doing computation, and that leads to thread leaks. Too many of these in your code lead to really, really nasty profiling scenarios where you have hundreds, maybe in worst cases that I've seen, thousands of threads in the background doing nothing, computing a result that will never be used. Zeo gives you a timeout that is extremely powerful. If you timeout an effect in Zeo, you get back a new effect that will terminate the old one when the specified amount of time has elapsed. So there are no leaks in resources. In fact, when you time it out, it won't even, the timeout operation, that effect won't even return until the previous effect has been terminated. That allows you to build applications that don't leak threads. And this is also asynchronous. It's 100% asynchronous. So it doesn't involve blocking a thread like the future-based equivalent. This efficient termination or efficient cancellation was incredibly important to building Twitter. That's one of the reasons that Twitter has their own future, because they needed the ability to cancel futures that weren't being used. It isn't baked into Future. It can never be baked into Future. It has the wrong shape of API for that type of feature. It's baked into Zeo, and you see it not just in await.result. where a termination will result in immediate cancellation of the underlying effect, but you see it in a bunch of other places, like Zeo's version of first completed of. So first completed of, if one of those fails, what happens is all of them continue executing until completion. Whereas in Zeo, if one of them fails, the rest of them are terminated immediately. Similarly, for things like sequence, if one of the things you're sequencing over fails, in a list of 1,000 things, all 1,000 futures will run fully to completion. And in Zeo, as soon as the first one fails, the other 1,000 will be immediately terminated. Another real drawback and complaint that people have when they're working with future-based code is that what happens when something goes wrong? The application blows up at runtime. If you've ever looked at a stack trace from future-based code, it looks something like that. And the interesting thing here is it doesn't contain a lot of information that helps us fix our problem. We see a lot about the guts of future, the internal implementation of future, but we don't see a lot about our code. And the reason for that is what happens is in future, every time you're doing an operation, it's submitted to the thread pool. That's a fresh entry, that's a fresh stack frame. And so the stack frames don't actually collect information about where your code is flat mapping. They actually collect information about the internals of future. Zeo has a feature called execution traces that will give you stack trace-like information. In fact, it's more descriptive than stack trace information because it tells you line by line, every flat map, every operation in your chain of operations will be captured as part of the execution trace. This gives you the ability to figure out what went wrong, which helps you fix it. Not only will these execution traces tell you everything that happened previously, but they'll actually tell you things that were going to happen if the code had not completed, had not failed. Future is not very refactor friendly. And what I mean by that is, let's say you're looking at a chunk of code over on the left-hand side here, and you see some duplication. One of the techniques that we can use to eliminate duplication is a refactoring called introduce variable. So we introduce a variable, and we take the duplicated expression, and we put it in the variable, and then we refer to it twice. And you can see I implemented that refactoring over on the right-hand side here. However, in so doing, I've actually changed the meaning of this program. These two programs, the one on the left and the one on the right, they don't actually do the same thing. They do totally different things. And that's because Future is not lazy. Future is not sufficiently lazy to enable us to refactor safely to our applications. But Zeo is totally lazy, which means when we take this same example and we factor out the duplication in our for comprehension and stick it into a local variable, these two programs do the exact same thing. That's the benefit of a lazy effect type like Zeo, is that you can refactor your code and you have a guarantee that its meaning will not change. You can introduce variables, you can eliminate them, you can introduce functions, you can eliminate them, you can change a def with no arguments into a val, and that will never change the meaning of your program. This helps you use all the refactorings you know and love on your whole program without having to think carefully, hey, am I actually going to break this or not? Future is also a little hostile to abstraction. So in abstraction, we see patterns, and we want to eliminate duplicated code. DRY, it's called, don't repeat yourself. So you might have run into a situation where you needed to retry a computation a bunch of times. And it would be great if you could write a retry combinator to do that. So let's say we try to write a retry combinator here for future that says, well, give me a future and the number of times to retry, and I'll give you back a future that does the first future the specified number of times. Very simple, right? We might want to do this to eliminate duplication. So we do this, and suddenly we discover this code doesn't do what we thought it would do. And the reason for that, again, is future is not sufficiently lazy. This code won't retry anything. And that's because futures are already running computations. They have no available mechanism to restart. Do the same thing with Zeo, and it works out of the box. Future has an error channel baked in. Oh, thank you. Future has an error channel baked in, which is great because programs fail. We need the ability to generate failures and to respond to them. The problem with the error channel in Future is that it's rigidly fixed to throwable. It doesn't change. It's made a choice that every single error you ever have will extend throwable. Like try, for example. Try makes the choice that every single error you ever have will extend throwable. Either does not make that choice. Either says you can change your error type if you want to. And even if you only ever use throwable, which is fine, that's what many people use all the time, what that means, practically speaking, is that when we recover errors from a future, the type of our future doesn't change. We started out in this example with a future of int, we handled all the errors, and we get back a future of an int. The compiler is not tracking the fact that we've handled all the errors. And we have no way to require that someone give us a future that can't fail. There's no way to write that constraint. So in some sense, Future is not really taking advantage of the power of a static type system. Zeo has a dynamic error channel, so you can plug any type you want into that. You can plug exception or throwable, or your own custom error type. You can even plug in nothing to indicate the absence of an error. And when you handle errors in your Zeo program, the type of those effects actually changes. The error goes away. You have static proof that your effect can no longer fail. And this can help you write applications where the error behavior is extremely well defined. Future has no construct in it to help us deal with resource safety. And our languages give us a construct. It's called try finally, or try with resources. But the problem with try finally and try with resources is that they weren't designed for modern applications. They're not asynchronous constructs. Try finally and try with resources, they only work on synchronous code. They're not going to work if you got a bunch of parallelism or asynchronous code in there. And Future, which would be the natural candidate to have something like this, it doesn't give us an operation like that. So if you actually write code that looks like that for comprehension, that opens some resource, it acquires a resource, it uses the resource, and then it closes it, eventually over sufficient amounts of time, you're going to exhaust all resources on the machine. And that's because Future doesn't give you a primitive to make resource-safe applications. Zeo gives you a primitive called bracket, which lets you safely acquire and release a resource and use it, and no matter what happens when you're using it, no matter what thing goes wrong, or even if the computation ends up being canceled, if the resource was acquired, it will be released. These are the strong guarantees you need to write applications that don't leak resources. Future has only a few operations in the data type, 21 operations in that and maybe the companion object. And these help you deal with very, very basic problems in parallelism and concurrency. But the problem is they're very low level and there's not very many combinators, which means that when you have a problem with a future, most likely you're either going to write more code on top of that yourself, or you're going to Google Stack Overflow and you're going to copy paste some code from Stack Overflow. Everyone out there is doing it, and that's because Future's way down here, but your business problem is way up here. And even though we really can't bridge the entire gap, what we can do is meet halfway and solve a bunch of the common problems people have inside the data type itself. And that's why Future only gives you 21 operations, but Zeo gives you actually quite a few, maybe too many. Maybe too many, but chances are, if there's something you want to do, for example, you want to retry, or you want to repeat, or you want to do safe resource cleanup and so forth, there's probably an operator that does exactly what you need with really great Scala docs and examples of how to use it. And that helps you solve the problems that you have faster. So I'll admit it, I'm a long-time Java programmer. I programmed in Java for probably 7 years before I found Scala. And I love Java util concurrent because what it gives us is the language, a toolkit, if you will, for solving problems with concurrent programming. Inside there, you're going to find things like concurrent hash map and concurrent queue and concurrent set semaphore and lock and condition variables and the atomic machinery, thread local, all that stuff comes out of the box, and it just works. And it's really good. It was written by really smart people who knew exactly what they were doing. And you can build some very powerful concurrent applications on top of this toolkit, but there's a problem. All that stuff inside Java Util Concurrent is blocking. It's 100% blocking. It does not integrate well with modern asynchronous applications. And Scala Concurrent Future, it has nothing to say about this, other than maybe use the Lightbend stack and use some actors to solve some of these problems. But Zeo gives you the same toolkit, more or less, actually a slightly more complete toolkit that Java Util Concurrent gives you. It gives you the concurrent map and the concurrent queue, concurrent set, the semaphore references that can be updated concurrently, a version of thread local that works for a fiber-based concurrency system, and even software transactional memory, which is an extraordinarily powerful way to think about building concurrent applications. You can actually specify, create transactions that make changes to different parts of state in your application, and you can commit them atomically, even in the presence of massive concurrency. And you can do that without race conditions and deadlocks. That's a game changer for building modern concurrent applications. And finally, point number 10, Future is not very performant. And the reason for that is, by default, every single operation on a Future will submit to the thread pool. And that means that a given core in your CPU is constantly transitioning back and forth between which future operation it's evaluating. That's catastrophic for performance. Catastrophic. And the reason why is that it's very expensive to fetch data from the main memory and get it all the way down to the CPU core. It takes a long time. And what happens is every time a core switches to a different thread, it's got to warm up its local cache of that information. So when it's switching all the time, it's actually not having a chance to build up any good cache. And everything has to be fetching stuff like crazy from main memory. Zeo, on the other hand, by default batches and allows these cores to warm up, executing a large number of operations sequentially on the exact same core before it defers to other computations that need to be run. And the end result is that you can achieve something that's 100 times faster using Zeo-based code. And that doesn't mean if you plug Zeo in, your application's actually going to be 100 times faster. This is a synthetic benchmark. But what it does demonstrate is that you can use something like Zeo, and you have to worry less about performance than ever before. If you worried about using Future too heavily in your application, it was probably a good thing. You don't have to worry about using Zeo too pervasively in your application, because it's managed to improve the margins by so much that it makes it practical to use it across your whole application. All right, let's briefly talk about upgrading. So if you're interested in giving Zeo a try, let's walk through a few examples of what that might look like. And I'll give you some tips on how you can do this. So first off, it's very simple to get started with Zeo. You just add that single line of, or 2 lines of code to your SBT build file. The first one's probably already there, so just add the library dependency on Zeo dev. And then here's your Hello World program. This Hello World program extends app, which is a data type in Zeo. And it implements a run function that takes a list of your command line arguments. And then inside that run function, we just return a lazy value. This would be the equivalent of returning a future, only we're not returning a future, we're returning a Zeo effect here. And then there's an additional line after that, which is calling .fold, and this is basically to fold over that value and turn the error into the number 1 and the success into the number 0, just because it's the main function, so we have to return an integer code out of there, so that if you're using it from the command line, other applications can tell whether or not it failed. So in this case, we just map all failures to 1 and all successes to 0. If we want to do a little bit more complicated example, then you notice here, I've switched to using a for comprehension. This is the single biggest pain point of either using Future or using Zeo, is learning how to use for comprehensions. And I will grant this is not obvious syntax, and you have to relearn a bit how you express common problems. But I promise you, you can do it, and it doesn't take too much time to become more familiar with the for comprehension syntax. And once you use the for comprehension, you just state everything you want to do in a linear order. What is your name? Get the name from the user, print it out to the console, and then return some value out of your for comprehension. That's the translation that you go through mentally when you use for comprehensions. And in this case, that produces an effect, and then I use the or else operator to say, well, if that effect fails, I want to do something else, namely I want to succeed with the number 1. So what happens is I either return 0 out of the first effect, which means success, or else I'm gonna end up returning 1 out of that. And you can see here, this is starting to lead us into a new way of programming. We're programming here with values. We use operators on values to create other values. And this is a little mind-bending. And it's what's truly mind-bending is when you see what power this gives you. You can solve in a few lines of Zeo code, you can solve something that would take pages of traditional procedural or object imperative code. Let's say we have some code like this and we want to convert it. It's pretty easy. The first thing we're going to do is we're going to change that type there. Instead of returning future, we're going to return a data type called task. That's the only change there. We'll change it to return task. And then the lines inside here, we're just going to linearize them and stick them inside a for comprehension. And then what we do is we create a little helper called logz, which just wraps our ordinary log function. And that allows us to return a task from that. So log, it returns a task. It didn't previously return a task, it returned a unit. Now it returns a task of a unit. And then what we do is we take make pending and we stick it inside task effect. It used to return task unit, but now when we stick it inside task effect, we'll get a task out of that, so we can stick it inside the for comprehension. We had a future there in charge, so we're just going to wrap that in task.fromFuture to convert the future into a task. And then finally we had mark complete, which is another one of these things that returned a unit. We just stuff it into task.effect. So basically you take the return types and depending on what they do, you either convert them to task using fromFuture or convert them to task using effect. And now we can just stick all these lines in a for comprehension and you can see the nice linear structure. And the linear structure was not so obvious in this formulation. That's because a lot of future code in the wild doesn't use for comprehensions. It uses something that's more like this because it's difficult to convert things like mark complete and so forth into futures. It's inefficient to do that. All right, so what have we seen from this example? Well, first off, if you're starting to use Zeo, experiment with task first. So there's only one effect type in Zeo, and it's actually not called task. It's called Zeo. But that type has a lot of power and you might not need it. So there's a type alias for you called task, and task is the simplest analog of future. So it's almost the same as future, and the type parameter has the same meaning. It either fails with a throwable or it succeeds with an A, and this task has no dependencies. Then what we do is, in any method that we're converting, we wrap the entire body by task.effectSuspend. And this allows us to take that eager code, that eager future-based code, and make it lazy, which is how we get a lot of the benefits of using Zeo. And then finally, anytime we're calling into code that used to return a future, we just take that future and we convert it into a task using task.fromFuture. There will be some points in our applications where we have to go the other way around. We've converted some code to using task, and now it expects a future, so we need to convert it to future. You can do that. You can't do that lazily, unfortunately. So future is not lazy. So anytime you convert from a Zeo task into a future, that's going to be non-lazy right there at the conversion point. It's going to kickstart that computation. And there are certain implications you have to be aware of when you're doing that. So that's why it's called unsafe run to future, is that it changes the programming model. And all the benefits of Zeo, they stop at the edge when you convert it to a future, because futures can't be canceled and all this other stuff. So you want to defer that as long as possible. But it is necessary and it's supported natively. in Zeo. Number 5, plan to never leave. So once you enter a Zeo effect type, you basically stay there. Ideally, in an ideal world, you stay there for the rest of your application. And the reason for that is, as I said before, anytime you run a Zeo effect, you convert something that's lazy into something that's eager. So you kickstart that computation. It changes how you think about your programs. It's no longer safe to do refactoring on futures and so forth. So it changes how you think about your programs, and also all the benefits of Zeo only go up to the boundary. So whenever you run a Zeo effect or convert it to a future, all the benefits stop there, which means you should try to keep as much of your code base inside Zeo as possible. And that's possible, by the way, because you can take tries and you can take futures, you can take eithers, you can take options, you can take all these different data types and you can convert them into a Zeo effect. So it enables you to take and lift everything up to the level of Zeo and program in Zeo for more of your application. And obviously this does not mean to stay with the library forever. Always use the best tool for the job, and if that stops being Zeo, then by all means switch away from it. Number 6, rewire your brain. So working with lazy effect types like Zeo, it changes the way you think about programming. Not overnight, but eventually it totally changes the way you think. You start thinking about every single thing in your application as an ordinary value. There are no more side effects anymore, there's just values. And what that means is that instead of running things, for example, in this picture, I have a picture of someone going running. That would be a future. It's something that's happening. But in the world of Zeo, there's nothing that's happening. Everything is a immutable value. So there's no one going running in Zeo. There's just descriptions of going running. And as a description of going running, all Zeo effects are first-class values. And this is what enables you to do refactoring safely. It's what enables you to write combinators like retry, which take one effect and return another one that does the effect of the first one a bunch of times. This is the key to a lot of power in Zeo, but it also means that you think differently about your application. If you construct a Zeo effect value in the middle of a method and you don't do anything with it, it's as if you didn't make it, because it's nothing more than a description. It doesn't actually do anything. And getting over that little bit of a hump, that hurdle from thinking of your programs as things that do things to things that describe things. They build almost like pipelines or data flows, if you will. They build those descriptions of things is the biggest hurdle that people have when they're using a purely functional library for effect management. Finally, Future solves the problems of asynchronous programming and parallelism reasonably well, not perfectly, as we've seen. There's some problems with its management, but that's pretty much it. And in Zeo, what Zeo really gives you is a fabric for building asynchronous and concurrent applications. Yes, you can eliminate callbacks in your code. And yes, you can use all cores in your machine. Yes, you can fix number of threads to be the number of cores on your machine. You can do powerful things like that that help you build modern applications. But Zeo also has a lot of other functionality in there designed to help you build modern applications that don't leak resources. They have well-behaved thread management, so they use thread pools appropriately. They have well-defined error management that's statically checked by the compiler. And they have the ability to do transactions across memory in a concurrent, safe, and deadlock-free fashion. So there's a lot of stuff in there. And it's not a ton of code, but there's a lot of stuff, and it helps you build modern applications that solve real-world problems more simply than ever before. So as we've seen, there's a monumentous shift happening in the industry caused by the death of Moore's Law way back in 2005 that's leading to things like Future being created. It led to Go routines, it led to Akka, it led to Kotlin coroutines. Basically, it's slowly changing languages and libraries. They're all changing to be asynchronous and concurrent, very parallel. And these are affecting all of us to one degree or another. Future helped us solve those problems early on, but it's a very old data type, and we've learned a lot about some of the drawbacks that it has and how to fix them. And that's where a library like Zeo comes into the scene and says, okay, well, let's build on what Future did. Let's come up with something that allows us to build modern applications, but with better resource safety, better error management, better thread handling, the ability to abstract over our code, the ability to refactor it safely without changing the meaning of our programs, the ability to test these things, and so forth. And that's what a library like Zeo gives us, is the ability to do everything the Future did, but better, because that's what we need. In modern application development, we can't escape it. The only question is which technology we'll choose to solve these problems. And then finally, at the end, we looked at how you could take a Future-based application and start experimenting with using Zeo. As should have been clear, I hope, from my examples, you don't have to do that all at once. It doesn't have to be a sort of big bang rewrite. You can actually introduce it in small little places. And you do that by wrapping code using effect suspend or effect. You just wrap it into task. At any point you have a Future, you just convert it into a task. And that allows you to start experimenting with Zeo in an existing code base. And we didn't cover it today, but there's a growing variety of libraries out there that are Zeo native. And these libraries help you solve problems from interacting with Kafka to using some Amazon services to logging and this and that. There's lots and lots of libraries sprouting up around different concerns. So there's a chance, especially if you're in a greenfield project, that you might not have to do a whole bunch of wrapping yourself. It's basically going to be, you can use Zeo native versions of a lot of the common bits of functionality that you're already using. And then anything inside the Cats Effect ecosystem, like if you've used Doobie or FS2 or other HTTP4S, all that stuff can be used seamlessly with Zeo because Zeo has Cats Effect instances. So if you're using something in that ecosystem, you can definitely benefit from Zeo right away. All right, so that's where Zeo is today. And there's one big challenge that we have not solved in Zeo. Zeo is a really powerful package for building async and concurrent systems. However, there's one really big challenge that we've not yet solved that hopefully we will solve in the next year, and that's going to be very exciting. I'll let you guess what that might be. All right, well, thank you for coming to my talk today. I hope to meet many of you out there and speak with you. I'll be around all day, so please come by and say hello. I'm also doing a workshop, an hour-long workshop, so if this is interesting enough to get started using Zeo, then please attend my workshop. We'll build a fun little application. And then I will also be back, hopefully, assuming there are no problems with my Russian visa, my next Russian visa. I will hopefully be back here in November to hang out with you all and talk more about Scala. So thank you for coming to my talk.
Thank you for the presentation. I think I have a quite common question. You are making a comparison of Zeo to old good Scala Future. What about a stronger opponent like Monix task? It's also lazy. It has baked-in cancellation, resource handling. Why should I take my application and rewrite it to Zeo? Did you do any performance testing? Thank you.
Yeah, great question. So the question was basically, okay, so Zeo is one of several next-generation effect systems in Scala. And the other two major ones are Cats.io and Monix. And the question is, well, if I'm already using Monix or Cats.io, is there a reason for me to use Zeo? And of course, the answer is always, well, is there? If you're using something and it's working for you and you're happy with that, then there's probably no reason to switch. So I think Zeo's innovated in a number of key ways. The fiber-based concurrency system, interruption, purely functional interruption, and other features that came to Zeo first. And so I think the project has demonstrated a lot of leadership and will continue to demonstrate leadership. And even to this day, there are benefits of using Zeo or design choices in Zeo that are not made by the other libraries. For example, Zeo, when you lock an effect to a given pool, you use lock. And what happens is it will always stay running inside that execution context. It's never going to jump off. If you try to do the same thing using Monix or Cats Effect, then it will execute in that thread pool until it hits the first asynchronous operation, at which point it will bounce off that thread pool and hop over to its default thread pool. And that means you never know for sure without analyzing your entire program where a given effect will run, because it could pop off and end up back on the default thread pool. Basically, you always need to explicitly shift. Every time you do async operation using Cat's.io or Monix, you need to explicitly shift back to the thread pool it's supposed to be locked on for it to do the correct thing. Another difference is execution traces. So Zeo is the only effect system out there to give you detailed diagnostics, line by line information on where things went wrong that goes across concurrent boundaries and parallelism. And that can prove a game changer for diagnosing problems in systems. Zeo also has the strongest resource management guarantees of any effect system. So if you bracket is also that primitive bracket for resource handling and another one called ensuring, they exist. They have their own equivalents in Cat's.io and in Monix, but they don't have the same semantics. So Zeo will always guarantee that your finalizers are called, always, 100% of the time. Whereas that's not true with Cat's.io and Monix. Actually, for example, if the effect that you're trying to add a finalizer to, if it joins a fiber that's interrupted, then it will hang forever and your finalizers won't be called. So lots of little choices like this, combined with Zeo's support for making your effects testable and for software transactional memory and so forth, I think create a compelling picture for why an application, especially like Greenfield, would want to at least experiment with Zeo before switching over. But at the same time, if you're using Cat's.io or Monix and you're happy with it, then there's probably no reason to switch. Stay with what works for you and your team. That's always the best advice. If something's working for you, I'm not a big fan of chasing shiny new things, even when they happen to be projects that I'm involved with. Like if something's working for you and your team, then just stick with it. Any other questions?
Thank you, John, for coming and delivering a great talk. And also thanks for building both Zeo and the great ecosystem around it. So I actually have two questions to you. The first is, are there any available memory and performance profilers that will help me to determine the level of parallelism I can get with Zeo? And the second question is, do you expect any API changes in Zeo when JVM community introduces its own green fibers? Thanks.
Yeah, really great questions. So first question, are there any tools to help us figure out what the optimum level of parallelism is at different points in our application? And the answer is no, there's not right now with the functional effect systems. But that's a really good sort of real world problem that I think that we'll try to address that problem and other types of problems post 1.0. So Zeo is actually not 1.0, it's almost 1.0, it's like a few weeks away from being 1.0. But after 1.0 gets outside the fence, so to speak, then we'll be able to spend more time addressing those types of concerns. And not just those, by the way, but there's a whole host of things that go into building and deploying these applications that we need to really tackle if we want to provide a viable alternative to threads, basically. And that's what we're trying to do. That's what Akka tried to do. That's what we're trying to do in the functional effect systems. Then we have to give people the tools necessary to monitor, to optimize, and debug. And that's an area where we're just so committed. I think you can see that in the execution traces. The Zeo community is very focused on the problems that we have day to day in using these things, and we want to fix them. We want to make it better. We want to make it possible and easy to write very good code using these systems. So not yet, but definitely look for that in the future. And if you're interested in being involved with it, then please reach out and we'll chat about it. The next question is, what was that again? Is
green threads.
Right. Yeah, so Project Loom is coming. This is one of these sort of changes that I mentioned. The whole world is changing. It's inescapable. The JVM itself is changing. The JVM will be getting fibers. And these fibers will be similar to the fibers in Zeo. Zeo has a fiber-based concurrency model, which allows you to run a lot of almost virtual threads, if you will, on a single JVM level thread. And in a similar fashion, Project Loom is introducing lightweight virtual threads that are going to allow you to run a whole bunch of them on a single JVM level thread. And it's our goal in the Zeo project to fully support Project Loom when it comes out. And even though obviously it's early tech, so it's hard to say for sure, most likely there will be no API changes involved. So Scala developers can hopefully just continue to use that stuff. And we are fully committed to maintaining backward compatibility for the 1.0 release. So once that comes out, then it should be good for a good long while before we introduce 2.0.
Okay, last question.
Last question.
Actually, I wanted to make a guess about blank lines, in your last slide. So will you go to compete Akka in terms of distributed computations? Can you give us a clue? What will it be? If I'm right, of course, if it's going to be a distributed computations, Zeo.
Yes, so I'm very, very excited to be working with some folks on basically Zeo distributed, on some early technology that will form the cornerstone of Zeo distributed. This will be a separate library, of course, built on Zeo, but my hope is, just like with Future, a lot of people have been using Akka for a while, and Akka clustering, it solves the problem, but there are some notable drawbacks. Akka clustering, applications have a lot of failure points when using that. There's a lot of sort of maintenance overhead. Even though the API is fine, there's still a lot of operational and maintenance overhead that goes into running an Akka cluster. So my goal is basically to learn from all of the experience that people have with Akka clustering and to package it up in a way that's more type safe, that helps the Scala compiler help you write correct code, and also more principled. So you have strong guarantees that when you go to write software, if the types all align, then it's going to work in production when distributed on a cluster. So more news about that coming soon. Not too soon, but definitely coming soon, because we're making good progress with that set of projects.
Thank you.
All right. Thank you so much.